By the late 1920s, physics was split between two incompatible frameworks. Einstein's relativity explained the massive and the fast, while quantum mechanics described the tiny world of the atom. Both theories were successful, yet they could not occupy the same space without the math breaking down. Paul Dirac sought to bridge this gap. While his contemporaries focused on physical observations, Dirac prioritized absolute mathematical consistency, believing that a sufficiently elegant equation would eventually reveal the physical truth. In 1928, Dirac derived an equation that successfully combined these two fields to describe the electron. However, the solution forced a choice between two mirrored paths, one representing positive energy and one representing negative energy. In science, equations usually describe what we already see. But Dirac's work suggested the opposite, that the logic of the math dictated the properties of the universe, even when those properties seem to contradict reality. Energy normally starts at zero, the state of a particle at rest, but Dirac's equation demanded a state far below zero, in a negative energy space. Because physical systems always seek the lowest energy, every electron would sink endlessly into this abyss, falling forever. If electrons were free to fall into these negative states, atoms would lose their structure. Every piece of matter would become unstable and instantly collapse. Since the universe remains intact, physicists faced a choice. Either Dirac's logic was flawed, or the physical vacuum operated under constraints that prevented this infinite energy descent. Dirac refused to discard his equation. He reasoned that if the math was correct, then our definition of empty space had to be wrong. He proposed the Dirac Sea, an invisible, infinite ocean of electrons completely occupying every negative energy state. Because it's full, regular electrons cannot fall, but a high-energy photon can knock an electron out, leaving a hole in the grid. This empty hole would behave like a physical particle. Because it represents a missing negative charge, it would appear to have a positive charge, while maintaining the exact mass and properties of an electron. Dirac used pure logic to deduce a symmetry woven into the fabric of space, predicting the existence of antimatter years before it was ever observed. Verifying this symmetry required a physical test. Researchers fired high-energy gamma-ray photons at a metal target, attempting to provide enough energy to lift a particle out of that theoretical sea. Based on Dirac's work, the photon's energy should split into two distinct particles of equal mass. In a magnetic field, their opposite charges would cause them to curve in opposite directions. In 1932, physicist Carl Anderson captured an event that matched this prediction exactly while studying cosmic rays in a cloud chamber. This image from Anderson's detector shows the evidence. The curvature of the track reveals the particle's mass, which was identical to an electron, but the direction of that curve, as noted here, proved the charge was positive. The impossible mathematical result was a physical reality. Antimatter was real. The discovery of antimatter introduced a new consequence. If these two particles are perfect mirrors of one another, we have to ask what happens when they meet in physical space. Inside a controlled detector, an electron and a positron are brought together at low speeds to observe their interaction. They do not collide like solid objects. Instead, they vanish completely. The matter and antimatter neutralize one another, converting their entire mass into a burst of pure energy. This event maps perfectly to Einstein's E equals mc squared. The mass of the two particles is converted into two gamma rays, each measuring 511 kilo-electron volts, the exact energy equivalent of an electron's mass. This annihilation demonstrates that the universe requires a perfect balance between matter and energy, maintaining the symmetry Dirac first saw in his equations. When we apply this principle of symmetry to the start of the universe, we encounter a massive contradiction. The Big Bang was a massive conversion of energy into mass. According to the laws of physics, this should have produced an exactly equal amount of matter and antimatter. Yet the observable universe, from the stars and distant galaxies to the atoms in our own bodies, is composed almost entirely of regular matter. This leaves modern physics with an unanswered question. Is matter and antimatter annihilate on contact, and they were created in equal amounts? Why does any matter exist at all? Dirac's work shows that mathematical equations can serve as predictive maps, revealing the hidden structures of nature long before we can see them. But in revealing those structures, they also expose the vast gaps in our understanding of how the universe survived its own creation.